So Christian Landles, he is a senior research associate in Jill Bates' lab, and he will present on novel bioassays to detect soluble and aggregated isoforms of the Huntington protein on 3 technology platforms. So Christian, it's your stage.
Thank you for the introduction. Yeah, so this is really an extension of the paper we published 2 years ago in Brain Communications, where over the last 5 years we've been developing assays to detect Huntington, and we used 3 platforms to do this on preclinical mouse models. And we were available to develop a number of assays to detect various forms of the Huntington protein, ranging from exon 1 through to total soluble mutant Huntington, and the full-length protein and various forms of aggregated Huntington. And this was to build on, as Jill explained yesterday, assays that were already in existence and to generate some new assays which we could apply to our mouse models. And so to do this, we originally had 6 antibodies spanning the Huntington protein, and we're now expanded on this to include some new ones such as S830, D7F7, 3B5H10, to really explore all the possible combinations of antibodies that we can use to generate assays to detect the Huntington protein. And we did this in collaboration with PerkinElmer and CysBio, and we developed this triage strategy where we went through a pipeline of optimizing these assays by starting really with the manufacturer's recommended testing conditions, where to start with we were able to just eliminate assays that had very little signal over background, or they didn't give, if there was a mutant-specific antibody, it gave no signal in the wild type. And what we found quite early on was this phenomenon of poly-Q tract interference, where many assays where you had an expanded repeat just did not work, particularly ones that crossed the repeat. So if you had an N-terminal antibody to somewhere else down the protein, it just, as you have a pathogenic repeat, the assay just failed. And as a positive control for this, we also brought in the YAC128 mouse, which is a transgenic mouse expressing a full-length copy, where we have 3 copies of this, of Huntington, 2 endogenous mouse and 1 extra full-length Huntington. And we could then develop the full-length assays because we have the ability to detect this 3rd copy. And so after navigating through all this, we could really come down to a finite small number of antibody pairings, which we could then challenge by developing assays where we challenge them for antibody concentration and titration optimizations, where we can eliminate more assays which didn't perform and give non-linear titration curves or had a very little signal window, or we had just alternative assays which were better. And then we had this final selection of antibodies which we then applied to the ZQ175 mouse to see how these assays worked. And so in terms of the optimization on the left here, top left, is a typical example of an assay. This is the exon 1 assay that Jill chatted about yesterday. And as you can see, we're looking in the wild type, we have no signal. We know exon 1 isn't made in wild type mice. And then we move to the ZQ175. We see at 2 months of age a significant level of the exon 1 protein, which diminishes with age as the protein's brought into aggregates. And so as opposed to the bottom left, where we can see there's an assay, this is also an exon 1 assay, but it's not so great. There's a signal in the wild type. There's not much window, and also the signal doesn't change with time. So as we then go from left to right, where we do the antibody titrations in the middle, followed by the lysate titrations at the end, we're looking for these linear titration curves where we know as we dilute the sample, we can see a change in Huntington signal. So if we want to go in with something like a Huntington lowering trial, we know we have the ability to see a change in the target. So it's important just to note that these assays are not quantitative because in the absence of matched poly-Q standard, this isn't possible. So any changes we see cannot be interpreted as fold change. And really, each bioassay, therefore, has to be individually optimized. So if we have a new mouse model with different repeat sizes, different levels of Huntington expression, we then have to do these titrations for every assay just to bring them into development in the model that we're actually going to apply them to. And in many cases, in the mouse models we have, we just don't have the poly-Q standards that exist to have, say, a Huntington with 200 repeats. So Jill talked nicely about the development of the MW8 assay, so I'm not going to spend too much time on this, but using the M171 mouse that doesn't make exon 1, we basically could confirm that we had an exon 1 specific assay for soluble Huntington, And then more recently this year, we've swapped out the MW8 with S830, and shown here in B at the bottom, we have a specific antibody to look for total aggregation and soluble. And then so finally, with the concept of polyQ tract interference, what we've developed here are some full-length assays where the top left shows that you can see Huntington doesn't change in all these mouse models. It's an allelic series of mice from Q20 up to the Q175, and as shown here, you can see with this assay, which is our best robust assay for full-length Huntington, we see no change in the levels of Huntington across all these different models across the allelic series. If you move over to the right, as you can see, if you have antibodies which span the repeat 2B7 to 2166, you can see on the same assay set, we see this reduction in signal with time. So there's no reason, why this would occur other than the assay just does not work. So as you increase the repeat, the performance of the assay goes down. And so when considering total full-length Huntington, you have to be careful about where you put your antibodies, and that was what was discussed this morning when we said the challenges of developing these assays. It really is important that we know where the antibodies are, because depending on where you put these antibodies, you may get different sets of data. So finally, we went to the 2B7MW1 assay. This is well known. Again, this is on the allelic series. We can see here, as over time, the expression. These are all done at 2 months of age, where there's no levels of aggregation, but we would expect to see a constant increase in this assay, but that's not what we observed, which was quite surprising. So with the 2B7MW1 assay, there seems to be a point around 80 repeats where we get a maximal signal, but then as we increase the repeat size, the signal actually then decreases. And this is not saturated, because we know in these homozygous lines we can see more. And finally, on the right, we have a human-specific assay which also suffers polyQ tract interference. As you can see here, using the 4C9 antibody, where there's no signal in the wild type, the assay performance goes down in the heterozygous and the homozygous lines as we add repeat sizes. So on that, I'd like to include this summary, which is just to say we developed these assays on 3 platforms. They're all roughly as sensitive as each other using these 3 platforms. They're not quantitative in the absence of a matched polyQ standard. Many of these assays have polyQ tract interference. Therefore, the interpretation of these assays are very complex and have to be taken with caution. And finally, I'd like to acknowledge everyone who's been part of this assay development over the last 5 years, including the CHDI who funded this. And I will end with these. Say, if you want further information, go to my brain communications paper, come to see me at poster D03, or any of the 3 other posters where you can see actually these assays being applied to real samples. Thank you.
Thank you, Christian. Do we have a quick question from the audience to Christian? That's a question? Yes?
Hi, Christian. Lovely presentation, and thank you for your, honesty with and perseverance in assessing the performance of these assays and developing these assays over such a long period of time. Just a quick question, do you think additional antibodies are needed? Do you think that's part of the issue?
Yes, I mean, now we have these assays, but it's very easy to now substitute in different antibodies. We've tried the Coaching and PHP antibodies recently, for example, as a substitute to MW1. So now we have these assays developed. Certainly, if anyone has an antibody that they think they wanted to try, that would be really good, because it's not too expensive to label these antibodies, and yeah, that would be good. Thank you.